Hey, good evening, everybody. Let's get started. This is day 9 of our class meeting, and we're supposed to review that memory usage, the first part of it, to understand how we load and store data into the memory and how we basically, what is the concept of this data, multi-byte data layout in terms of endianness. That concept is also important, and we reviewed that in this lecture. I saw one question from Mr. Jang about this difference between Mars static data and MIP static data. Uh, that's a good question. That's a good question. It's somewhat little bit confusing with respect to Mars as it use things. So Mars differentiate between two types of data. One is the local constant data, which is like dot data statement or anything. And there is also a concept of the global constant or global data, not constant. I won't say it's a constant, it's a global data. So local static data and global static data, Mars differentiate between them and added some like separate uh, memory segment, reserved memory segment, separate memory segment to store them. Let me try to explain it in bit detail. I'm sharing my screen. Okay, and so basically what we are talking about is this one, right? We wanted to have, like, this is the right hand side. What it is showing is that MIPS MIPS assumption or MIPS recommendation of usage different segment of the memory, and it does not differentiate between global static data and the local static data, or in a sense global static variable or local static variable. It just clubbed into this part, saying that from 1000 like 100, this is a hex, by the way. It is 1000 from there. It's a static data, and let me see if it actually shows the boundary, upper boundary of that. It should be somewhere in the green sheet. So this is your memory green sheet, the first page of your book. And here, oh, okay. So it's basically says that from this address to this address, it's about storing static data, and after that everything becomes dynamic. However, for the Mars, what it does, it uses this space, this address space. So it does not stop till 800. It goes beyond that until the entire part, almost like 64 kilobyte, is reserved for the global variable. I'll come to the concept of the global variable later. In fact, like I think 1 or 2 lecture down the line, we have one example of what is a global label or global variable means in terms of assembly language. There it will be discussing more detail, but I will touch base today also on this part. But what the Mars does in terms of the local static data, which means, like, let's say you are writing a program in Mars assembly, let's say like this, like, and you are just defined a variable var1 level and storing a word there at that, whatever that address location is. Now, if you assemble it, you see that it's that variable address, that variable label has been assigned an address with 10010000. So that's the start of anything, any statement that you want to make it. It would become like that, like dot data, under dot data, anything local you are trying to do would be like this. So which is basically, you see, like, it's after this address. This is the upper bound of the global variable address, and it is after that address. The very next byte address would be 1001,000, like 0000. So if you add 1 on top of this address, it's basically this address. So it starts from that, and there it reserves some part. How do we know how much it reserves? What you can do, you can go to tools, maybe settings, memory configuration. Here, it basically talks all about how the Mars as a simulator uses the memory space. So you see that global pointer is at 1000, 8000, that's address. And it's a data segment base address is from that 1000 and 0000. And then dot data base address starts from 1001,000. So this is dot data base address means, oh, okay, I cannot switch it. It's, let me just switch it here. So this dot data, so whenever you are starting that dot data segment, it start assigning addresses to the labels from this address. And how long it goes? It goes just below this address. This is the heap base address, which is like the dynamic data area where that heap allocation happens, from which address heap allocation happens. So it will be just one below this part, which means it would be 1003 FFFF. So from 1001,0000 till 1003 FFFF, that segment is used to store all the local static variable that you define in your program, which is in terms of assembly program, it's just a label under the data segment, dot data segment. Yeah, that, is that kind of clear to you, or anyone else has any?
So basically means the Mars, the static data is bigger than the MIPS static data memory.
Yes.
And the bigger part, like the extra part, because on the Mars static data memory, they have like global and dot data difference.
Yes, they are the difference. And by the way, just one thing to mention, that when the MIPS gives you this convention process, it is just a convention of memory usage that's suggested by the MIPS processor. It is ultimately on operating system or whoever is programming the system, it's that system convention. It's nothing like, no hardware level or chip level feature is preventing anyone to use any part of the memory for any other usage.
Okay, got it. Thank you.
Okay. So your MIPS, so this part is basically MIPS suggested memory allocation strategy. But again, like whatever operating system is loaded on top of this hardware system, it's up to them to how it go and divide things up into the memory allocation. And Mars decided to do in its own way, a little bit own way for its some of the advantage it can take on this. So one experiment I'd like to do here.
Professor?
Yes, Rahul.
Yeah, I had a question regarding the load and store commands that that were explained in the lecture.
Yes, Rahul, I'll come to you. Just let me
All right.
this topic. Okay. So I just want to see if I just try to make it a global, then what happens? Just as an experiment. So what I can do, I can mark this guy as global, global var1. Then how MIPS, question is how MIPS assign these things. Still assigned like that. Okay, I need to see. Like, okay, I'll get back with the global things later. Okay, just give me some minute. Maybe next day. Just remind me. We need to do some experiment with the global and how we can use that data space. Do I actually do here? Controls. Now still 1001. I need to see. Okay. Now, in this respect, I would like to explain some more about this. Why? What is a global variable means, and why it is important to have an address space from this to this, assuming the global pointer power up address is 10008000 hex. So first of all, the global variable by concept is something like this. Like we can have, remember, like we can have like multiple assemble program. It is piece of code, multiple piece of code in an implementation, and then we can actually generate multiple object code by assembling each of these individual assembly file, and then link those object file together, make an executable. So in that concept, let's say I have one assembly file, let's say src1.asm, and another assembly file, src2.asm, and let's say there is a storage, like, and let me just draw some memory. Let's say this is a memory, and this part is referred by a label called, let's say, gvar1. Okay, and this gvar1 is defined as this src1.asm. So this file has that gvar defined, means that it has the label definition and maybe some word being stored there, something like that. But src2 wants to refer, so this guy defines the store, and src2 wants to refer to that part. And it can do that without defining that label locally inside that code. It can just do something like, okay, store word dollar maybe T0 to gvar1. Okay, so by the way, this is a pseudocode, and pseudo instruction. Pseudo instruction. I should say pseudo instruction. This instruction is modified by the assembler through some primitive set of instruction it uses, but ultimately it means that stored the variable, stored the value stored in that in this T0 register, whatever that value is, stored in this address, refer to that address and stored there. So that's the concept of the global variable, that it can globally access from any set of the assembly program, individual assembly program, which are linked together to make one single executable. So that's the concept of the global static variable. Now, the significance of having this like a variable, like a space, like a memory space, starting from 1000000 in a hex till 1000FFFF with global pointer set at somewhere in the middle. It's in the middle, which is 10008000, which is at the middle. And that means, and you see like this part is 64 kilobyte space. So that means individually it has a 32K, each of them.
Professor,
Yes.
your Mars, your Mars PowerPoint
Oh, sorry.
window is kind of covering it.
Oh yeah, I just realized that. Thank you very much for notifying me. So these two parts, so basically this whole part is 64 kb with a middle address, midpoint is addressed by the global pointer register. With that configuration, what a program can do actually, it can make something like memory references, let's say load one, load word, S1, uh, with respect to the global pointer and some indices, like maybe like, okay, uh, 24 plus 24. But which means what? Exactly this means add on top of this address an index value of 24. So it will become something somewhere here, a little bit increase point, right? And access that. Also, we can do something like S2 minus, let's say 28 with respect to GP. And that we can, that means it is lower address from whatever is pointed by this global pointer 800. So it will be somewhere here. And you see this part, both of them, this is the immediate part, right? This is the immediate part of the value. So which is like 16-bit, right? So as an index, you can actually make an index farthest as minus 2 to the power 15 to 2 to the power 15 minus 1. That is the value range you can access there, right? And with this range of indices, what it can be done is that without changing the global pointer at any point of time, you can access the end. You can either go to the farthest positive index or you can go to the lowest negative index that you can use. So you can actually access the entire space, 64 kilobyte space, without changing the global pointer at all. Just keep the global pointer at the middle, and just by changing the indices of where you are, that all indices are offset, either positive offset or negative offset, you should be able to access the entire space. So that's the significance of Mars placing the global pointer at the middle and allocating this whole part as a global static variable, so that each part of this different source code can access the data from here without suffering of any other performance issues. It doesn't need to change any other register. It can use the standard global pointer register to access the global static variable. So that helps in the performance improvement on your assembly program. Is that clear? Any question on that concept?
Yes. Other question?
Yes, Rahul.
The question actually built upon what you just explained, and it's a question about what was there in the lecture. In the lecture, for one of the, for two instructions, you had shown that the pseudo instruction can be translated into multiple different instructions if the immediate address, if the immediate value in that pseudo instruction you showed us cannot be accessed. I don't understand how does the situation arise where the immediate value is not enough to access the location that we want to access, considering that you just now showed us that we can access the full thing using any 16-bit immediate value.
So remember, this part is like, this is the just a fragment of the memory, right? You have moved
Yes.
memory upward. There are like local static variable, there are dynamic heap, and there are stacks.
Yes.
So then you won't be able to use this global pointer with this value at least to
Hmm.
access everything of above this point, right? So
Okay.
your indices, positive indices are bound, like you have limitation of defining this index. So this goes maximum till here you can access, or minimum till here. So you cannot access with this value as a base value. You cannot access beyond this point.
Hmm.
So that's why like it basically that happens. That's what happens, and I'm not sure if I answered your question or not.
It it does answer it, but then my question I'm understanding this a bit better, but
Mhm.
then what if you're going to try to access the memory locations above or below, aren't there other pointers for the above below locations? Like global pointer is not the only one. Don't the others work?
Right. So global pointer, like let's say we talk about the static. Right? Now let's talk about the static. Let's say it is local static is above here. Right. So how do we access it? Local static, we access it at some point of time that we set up some base register, and with respect to that base register, it does it. For example, let's do that once more, the experiment with the Mars. Let's say I want to access this guy. Okay, let's say store word. Uh, no, first of all, let me load some word. Add I dollar zero zero 39. Let's say. Okay. And then I want to store this into that var1. So now this becomes a pseudocode. Okay, my intention in this code is basically to store the value 39 into this address, memory address. Correspond to this memory address. I'm just referring to that address with some label name. Now let's see what it does. Now see here, it basically made that store word S0 var1 into two parts. One is setting up a $1, which is assembler temporary. And then with respect to that, it's storing into, with indices, it's stored into that area. This may not be a interesting example. Let's say, let me just put another, that 2. Okay, now let's see what it does. There you go. So what it does, let's say, so first it goes and execute this instruction, which changed the S0 to with that stored the value 39, which is in hex is 27. And then it goes and set up the assembler temporary with 1001.000, which is a base address, of starting of this local static variable. And then next, what it does, it uses that register as a base register and add an indices 4 on top of that and access that memory. Now you see at that location, it actually store the value hex 27, which is 39 in decimal, stored that value. So this is the mechanism it follows whenever you have a pseudocode like this. Make sense, Rahul?
Yeah, I see. That
So,
makes sense.
so that means if we go back to our global variable accessing, if we don't want to use global standard global pointer, then we have to do something like this every time. So one extra instruction per access of this global static area. And when a high level program is translated into a lower level assembly program, like multiple component, multiple assembly program split out, it heavily uh, it heavily rely on the fact that they can see each other's memory space through this global static space. So that means they access this global static space much more frequently than a global static local data. And that's where this optimization comes in place, that all these different parts of the program can access this space, global space from each other, just using the global pointer as a base register. And they don't need to do this double computation during the execution. And that's where it basically saves the runtime, it improves the performance.
Hmm. Uh, I think I'm getting the picture. And okay, so two more things. One, short things. The global pointer and the other pointers, by convention, we don't change their values, right?
Global pointer, we don't change the value. Stack pointer, we definitely need to change the value within. But global,
Yeah,
no, we don't.
global pointer we don't.
Mhm.
And the heap in the
Mhm.
stack section, the heap is also in the stack area, but from the other side.
Right.
Yeah. Do we use any particular pointer for that, or do we just say stack pointer modify go this much ahead or this much behind, or
With
global pointer go this much ahead and this much behind?
Okay, so within the assembly programming itself, we don't use the dynamic allocation that much.
Ah,
So
I see.
all we care about the stack processing and stuff like that. However, the operating system, when it runs on top of the hardware, it needs to know that convention, that what is my lowest address space from where I can start allocating dynamically the memories, and it keeps track of that. So it doesn't have any special register for that pointer, but from the hardware spec, operating system knows that okay, this is the convention and this is where I want to start my dynamic allocation start. So it's basically operating system keeps track of that addresses.
I see. And the final thing, a homework which is due today night,
Mhm.
it also has it also covers things of job or the next lecture, right? Because
Uh,
it's listed as a prerequisite. And I was confused. We're going to be covering that lecture stuff after the homework is due.
Yeah, we had to check module 9 before we could get the homework
so
assignment.
you're talking about the programming assignment
Two, yes. So
2.
were we expected to finish the module 9 on our own and then apply it in the homework?
Uh, Programming assignment 2 is nothing to do with the memory. Let me check. Just hold on. Programming assignment. I'm looking at that. Assignment. Where is that? Assignment. Doo-doo-doo. Let me see. This is the one, right?
That's the one.
Yeah.
Okay. So
It's just that we weren't allowed to look at the assignment until we looked at module 9. I think it's a thing with Canvas.
yeah. Swap print high low. And this one is module 3. Yeah, so this one is more related to the previous lecture, high and low, this part. Why do you think you need the next lecture for this one?
Because Canvas lists them as prerequisites for this assignment. We are not allowed to open this assignment until we've viewed the previous lectures.
Oh, really? Okay, let me see.
Yes.
Let me check. Ta-da-da. Move through 1, 2, 3, 4. These. Hey, I'm not sure why it is something like that. What you can do, you can actually click on this page. Click on this page.
And then just use it.
Yeah, just it will mark
Okay.
you that this is completed and then go back to that assignment. I'm
Okay.
not sure. Yeah, it was not my intention actually to do that.
So we don't have to apply concepts from this
No.
lecture and the next lecture for that.
No, not at all. This is purely based on your previous lecture, the register. So this
I see.
is all about like asking like how do you like this is entering a number like, and how do you take that value, user entered value into the high register, and then ask another number low, and how do you take that value, user input value, into the low register. So you need to use a move high, move low, that command, that instruction. And then you need to have a swapping macro which swap the value between high and low. So you need to use that move to the high and low, that instruction in a combination to make that happen. And you need to actually refer to the strings to print the statement correctly, and so on and so forth. So nothing to do with the memory access on this program.
I see.
Okay.
Hi, Professor.
Yes.
I have a question for the global variable. Can you back to the whiteboard again?
Yes.
So basically, you think the global variable is a signed number from -2 of the power 15 to 2 of the power 15 minus 1. Does a global variable can use unsigned variable, the unsigned number?
So basically, this is what I'm showing here is the indices, is the offset with respect to the global pointer. Okay? Now what is being stored here is purely like binary bit pattern. Like there is nothing called signed, unsigned, etc., etc. Like I'm just trying to pick up a binary bit pattern from this and store here. Now that's a very interesting concept that you asked, and let me clarify. Like it is up to the software program how to interpret that patterns of bit, whether to interpret as an unsigned value or signed value or a bunch of characters, bunch of letters, is solely up to the high level program to determine that usage of the patterns. Okay,
so basically, okay, gotcha.
Yeah. So at the low level, there is nothing called assigned, unsigned, etc. Like let's say, for example, if you use this, let's say, okay, let me just put some bit pattern, 1001 0001. Okay. Now this one, if you use that bit pattern into some instruction like add, okay, somehow like you get that. Now this add instruction conceptually it operates on the signed value. So that means that you need to interpret, or system need to interpret these bit pattern as a signed value, which becomes probably a negative value in this sense. Let's say it is a 8-bit 2's complement form, then it's a negative value. But if you use the same bit pattern with respect to unsigned operation at U, for example, then this same bit pattern is treated as an unsigned value. Okay, and then if you want to operate this same bit pattern as a bitwise operator, so individual bits will be considered in that operation. Okay, and also later you will see, like when we deal with the string characters, etc., they are also nothing but bit patterns corresponding to their ASCII code, and it is up to the program to determine or use like what to do with those patterns, how to interpret those patterns as a character, list of string, etc. But at the very low level, everything is bit, like 1 and 0. That's what it stores.
Okay, thank you. Got it.
Okay. What else? All right. Then what we can do, we can, let me see, I have some interesting question to ask to see some of you if you are prepared with content so far. Let me see who are here. Aditya, I have a question for you. Aditya Gutala, I think you are present. Yeah.
Yeah,
can you tell us what is a register file?
Register file is it's a sorry, I forgot the formal definition.
No, whatever you understand. I don't need a formal definition.
Oh, it's it contains like bits and
So is it a part of the processor or is it a part of the memory system?
it's part of the memory system.
Actually, no, it's a part of the processor.
Oh.
A register file is a combination of register storage, which are very fast and very close to this inside the process. Since it is inside the processor, access speed is really high, and assembly program uses them often, bypassing the memory access to save runtime. So we have like 32 register as a cluster inside the MIPS processor, and together we call it a register file. Okay.
Okay.
All right. Then let me see. Is it Chengwei Jiang? Can I see? Yeah, Chengwei Jiang is here. Chengwei, can you tell us like which one is the read-only register in the MIPS register file?
Sorry, I have no idea.
Okay. So basically, you can write any register with this li pseudo instruction or add I, as I showed earlier. You can write on any register except for the register number 0, which is a constant, which is the only register that you can only read, and it store a value 0. Okay. Is there Hong Nguyen?
Me?
Fong, not Fong.
Fong like PH or?
Not Fong.
Okay, thank
I
you.
am looking for Quinlan Hong Won Nigmin.
Hi. Yeah.
Oh, you are here. Okay.
Yeah.
Let's see. Hey, can you tell us a special purpose register and what's its purpose?
Yeah, so it's a register within the microprocessor, which pretty much controls the microprocessor's function.
Okay. Do you know can you tell us the name of it?
Like an SPR or
No,
uh,
SP is not a special purpose. It's a general purpose. It has a meaning given by the software convention, but it's not a special purpose register.
I'm not sure then.
Okay, this is a tricky question. So this 32 register in the register file, what I mentioned, they are basically treated as a general purpose register. There are special purpose register like high, low, and program counter. Okay, program counter you cannot access it directly. Okay, you cannot read or write it directly. High and low, you have a special instruction: move MF high, MF low, empty high, empty low. These 4 instructions are there, specialized instruction to read and write on those 2 register, high and low register. The purpose, program counter purpose, probably you all understand, it's basically keeps track of the next address to the next instruction, whereas your high and low, these 2 registers are actually holds the multiplication result and division result. Why so? Multiplication result is 64-bit result. If you multiply 2 32-bit value, it always results in 64-bit. Since the general purpose register are all 32-bit, this multiplication instruction has a special arrangement within the processor that its results are stored into the high and low register, the native multiplication instructions result. And then it's the software's duty to access those registers value, high and low value, and to manipulate the values further. For 32-bit systems, if the value becomes more than 32-bit, it's probably causes exception from the operating system. But if it is a 64-bit register, that's a different story. For the division operation, it also uses high and low because the integer division operation has 2 results. One is quotient and other is remainder. Okay, so you probably are familiar with a slash, which is a div operation and in the high level, and the mod operation, modulus operation, which is denoted usually in the high level with a percentage. Like A%B means A mod B, A modulus B, which practically calculate the remainder value of a division. But lower level div always create integer division, always create these 2 results, quotient and the remainder, and these are stored into these 2 special register, high and low register. Okay, all right. Alexander ONG, are you here? Alexander ONG.
Hello?
Yeah, hey, Alex. Can you tell us what's the MIPS assembly instruction to load the upper 16-bit of a register?
I'm not sure.
It's called LUI, load upper immediate, LUI instruction that is being used to load the upper 16-bit of our general purpose register. Okay. All right, let's take 5-minute break and we'll be back.
Professor?
Yes.
Oh, okay, fine. I'll ask after the break.
Okay, sure. We'll see you on after break then. Okay, let's get back. Rahul, you have some question before you went to break. Rahul, you are muted.
Do you mind if I ask, if I can ask a quick question, Professor?
Oh, yeah, Brian, yes, sure.
Yeah, so I finished the assignment 2 last night, and I had a conceptual question about the swapping method. So in high-level languages, you swap using a temporary variable, right? You like assign one thing, then you say, you know. Could we do the same thing in machine code or assembly, where we could set like high as low, and then set low as like a temporary?
Yeah, sure. Yeah,
Okay.
that's the way you need to do. Anyway.
Because like in the example you gave for the assignment, you said like put in like 2 registers, and then you take out the 2 registers with high and low.
No, that's a suggestion. You can do it in any way.
Okay.
As long as it's swapping, you're fine.
So it's possible to put like the high and into the low register, low into high register. Okay.
All right, Professor, am I audible?
Yes.
Yeah, my question was in naming conventions and how instructions are named and how they are spoken.
Okay.
So anytime we're taking data, is it always spoken in the sense of is the statements always framed in the sense of loading data into a register file? Because at least how I've heard statements, if you're talking about a statement where you're taking data from one register file and putting it in another, it's always it said like load R1 into R2. Then when we're talking about the moving from memory or moving from a register file to storage, it's or actually the other way around. When you're taking storage into memory, storage into register file, you say load load storage address into memory. And when we're talking about from register file to storage, it's and that's the only situation where I've seen store written, where I've seen store being used. So are there any
yes, store is more like in a sense of memory. Like it's for register, it is always a loading register with some values if you're changing that.
All right.
If you are reading from the register, it is just reading from the register. For the memory, it is reading from the memory and storing into the memory.
Okay. So if store is used, it does not refer to memory. It's a safe bet to say store for memory. Load is not for memory.
Yeah, it's not a very formal like grammatical thing. It's more like the preference, right? You can of course prefer to use something like a store this value to register. It is nothing wrong with that statement. It is just that I used to do that in that way, just to differentiate the fact that store is used for the memory in the sense there is a specialized instruction that store word, right? Anything else, like if you look at the set of instruction in your mixed green sheet, all this register bound operation has a part of has a couple of 1 or 2 register that you are reading from, and another register where you are actually storing or loading that register with the result, right? So maybe I picked up that convention in that way and I continue with that, but storing into register is nothing wrong there.
Okay. Thank you.
Okay. Now, why don't we?
Wait, Professor?
Yes.
Yeah, a question. The high address and low address, they're both 32-bit, right? Same as all the other addresses?
High register and low register, you mean?
Yeah.
Yes,
they're both
32 bits each.
Okay, and then when we have a multiplication result, you get a 64-bit result, you use the high and low combined together to store that result.
Right, exactly.
I see, okay.
Okay, now let's do a problem in group. Let me just first give the problem on the whiteboard. So this problem says like this. It's a 32-bit system which has the following in the main memory, byte addressable memory, content from the address, why it is, okay, here. From the address this is the starting address, and it stores the address in the increasing order like this. So whenever we talk about storing into the memory from an address, multi-byte information, they always goes from lower address to higher address. It never comes from the address to the lower address. Okay, the storing sequence is always from lower to higher. So we start from this address. So this address stores this guy, and the next higher address, like +1 of this address, stores that one, and so on and so forth. Now you are using a load word T0 with a offset 0 with the base register S0. Assume the S0 has this value. Now what after you basically execute this instruction, what would be the value loaded into the T0 register if your system is a big endian system? And other way, what would be if your system was little endian system, then what would be the value stored in the T0? By the value, you don't need to convert into the decimal or anything. Just give us the hex pattern there. Okay. So with that, let me open up. First of all, let me enable the share screen so that you can share screen with each other. And let me open up the what is called breakout room. Where is that? Here. Let's see. Okay, let's take 10 minutes for this problem, and then we'll come back to discuss that. And there are some, I see there are some room with one people. I'll probably send them to the other room to make sure you guys, at least you have one more partner to work in the group. All right, let me open the room for all of you. Okay, I think everyone is back from the discussion. Let's turn to group. How about SG9, study group 9? Do you want to share your discussion? What did you think about that? Study group 9, Chengwei Jiang, Quinlan Huang, Quinlan Nguyen, and Chengwei Jiang. Did you guys come to a conclusion on this problem? Study group 9?
Sorry, we couldn't get this problem.
You couldn't get this problem? Okay. How about the study group 1? Let me turn to them. Alexander Wenji, Karin Tang.
I had an idea, but I don't think it was correct.
No, that's fine. You can share your ideas and thought process.
So I don't know if this is like the correct process, but I just like imagine the address values like from part A in the main memory, and then I looked at the I guess address value of S0 in part B, and then I just like applied the definition for big endian system and little endian system.
Okay.
But
So
then
what's your final outcome on that part?
I'm pretty sure it's incorrect. So
no, let's just see.
Okay. I got hex C7 9A BC 875D6A for big endian.
Okay.
And then little endian, I got hex 87 BC 9A C7A523.
A5. So you started with 87?
Yeah, but I might have messed up the flip.
You're almost there. Like it's on the big, so little endian system starts, its convention is that lower address is the lower byte. So that means it's always by the load word is a 4 byte. So 4 byte will be loaded, but question is in what sequence? For big endian system, your lower address contains the higher byte. So your value loaded would be C7, 9A, BC, 87, which you are correct. Little endian, it's the same 4 byte, but in opposite sequence. It's the 87, BC, 9A, C7. Okay, I think you came to almost right conclusion there. Only you added extra A523, which is like beyond 4 byte. Okay, let me try to show it on this whiteboard, that problem, and see if you agree with that solution. Let me share it. Share the screen, whiteboard, share. Okay. So here, first of all, we need to put out these addresses, right? So let's do that. So we start from this address. And which contains 0x23, hex 23. Okay. So let me just say this number to caption. Okay. Now, so your next address, next higher address, I like to go from lower to higher as a address order, which will be EF, and it would contain F5. Okay, so it's because like this order I am going from lower to higher. So similarly, next address, which will become plus one of these, which is F0, which will contain C7. Okay, and then plus one, this will contain 9A. Then next higher address 2, which will be BC, and then next higher address F3 will contain 87. Similarly, for the storage, F4 will contain 5D. And next one, the last one, F5, oops, will contain 6A. Okay, so this is the memory layout. This is the whole memory layout under consideration. And now this load word is accessing an address starting with a base register S0 with offset 0. So this base register S0 is given at hex 4001 00F0 with an offset of 0. So we need to add on top of that. So my address accessed is $S0 plus 0, which is nothing but the same value as the S0 contains, 400, oops, 0 hex, which is hex 4001 00F0, which is basically this address, right? An address access from a given address always goes in a higher direction. So memory will be accessed for the load word for the next upper 4 bytes, which is like these 4. So now question become which way? So there comes your endianness concept. Big endian system says that my lower address has the higher byte. So big endian system, big endian means lower address contains higher byte. So that means this is my higher byte, then next lower, next lower, next lower. So my access content would be C7 9A BC 87. For little endian concept, LE, okay, let me change the color. For little endian is the lower address contains lower byte. So that means my higher byte would be this one, then lower is this, lower is this, lower is this. That means at the end of the day, we are going to load 87 BC 9A C7 onto T0 if it is a little endian system. So I think, yeah, I think that's the answer, and I'm actually overboard of the time. I hope everyone agrees with this answer, and For the next day, it goes into the very important discussion about the alignment of the memory. Please make sure you guys watch the video and grasp the concept. Very, very interesting concept and very, very important concept called alignment. All right. Is there any other question? Then let's close this class. Sorry for this 5 minutes late, more go overboard on this. So see you on next week then. And remember about the assignment.